half of the class doing the lesson and the second half of the class doing the homework. Now, I'm going to go ahead and dive in, even though I know we're missing some people at the lockers and whatever. Those of you that were gone yesterday missed a Desmos activity. That was pretty fun. You can do it. I can open it back up like next week when we actually have AO extensions, whatever. I can open it back up, but you essentially just missed an activity dealing with slope and y-intercepts. We today are going to continue that. We're going to do a review day next week. So any people that have missed things for school visits, stuff like that, yeah, the videos are available for you to watch. You can copy some of these notes, but we will also review things together. Okay, we will go over closure, do all that. I had your tests done, but I'm not giving them back today because there's no time. So we will go over those next week as well. First thing we wanted to talk about is make sure that we are comfortable with what slope is, and we write a definition in our notes. So I would like you to please just write slope. And I'm going to give you a couple representations of it. It's the vertical change over the horizontal change. Vertical change over the horizontal change. Another way we talk about it, though, is y2 minus y1. Notice I'm not just copying what the book has, guys, so please write down what I have. And another way, which relates to our Friday Greek schedule, is delta y over delta x. Now, in the old days of math instruction, we would have started this chapter by saying, okay, kids, here's this idea of this thing called slope. It is the delta y over the delta x. You subtract to find that. Let's compute 90 of these to make sure you can. In the new age of teaching math, we've spent days exploring, discovering, realizing that positive slopes, as they get bigger, get steeper. As they turn into fractions, lay down closer to the horizontal line. As they turn negative, point down. As they move left to right, which my arm's backwards for you guys, so I'm visualizing it in my head. We've discovered all of this. So now we want the formal in our notes, but not as here, you have to memorize this to know what this is. You know what slope is, right? We've already discovered this. We've already figured this out. Yesterday's activity, we were landing planes on landing strips. So if you were gone yesterday, I will reopen that activity next week when we have AO and extensions available that you can work on it. But we've spent a lot of time discovering all this. Now we're going to formally use it. Now today's lesson deals with proportional relationships. So while we're taking just some formal notes, a proportional equation is different than a linear equation. So I want you somewhere to write proportional because that's really critical here. Oh, yeah. Proportional, sorry. There's an R there. My brain is just apparently... You don't have to write that. But what we're often used to, and what a lot of you have started to just be able to spout out real fast, is saying y equals mx plus b. But in a proportional relationship, that doesn't exist. So today, what we're discussing is proportional equations. We will not see anything plus or minus after the mx. And we'll talk about why as we dig into this. I just wanted you to have a couple things formal on your notes before we dig in.
We'll talk about
So, political polling was a pretty hot topic here, a couple years ago with that whole, presidential election thing that happened. And one of the things that happens when political polls are going on is people called pollsters, well, it depends on actually who they are, people survey, right? So I'm not going to try to formally talk about names of people in order. People do surveys to try to make predictions. Actually, based off that, they decide where to spend their money. So a state that has already essentially been determined to go Trump, right? Trump isn't going to spend a bunch of money running ads there because they've already decided they're going to vote for him. But a state that's like on the fence, or a state that is more leaning the other way, a politician would want to spend their money running ads there to try to swing those votes back towards them. So often surveyors, and this is why we talk about statistics and things like that, surveyors will go ask a certain amount of people a question, and based off that, you go to make long-term predictions, or like extend that to, well, if this, then that. So, hang on just a second. So, in this situation, yeah, pollsters. So they called 100 random potential voters, and this is when they, like, if you've ever seen ads like, volunteer for the campaign, this is like what you would do probably. So they call 100 people just randomly, like, out of the phone book. And they ask them, hey, are you going to vote for Mr. Myers? Or Mr. Mears? And first they call 50. And of those 50, 34 people, my bad, say that they're going to vote for Mr. Mears. When we look at that data, we say, well, okay, 34 out of 50, that would be 68%, right? If we talk about, like, if it was out of 100. Are we with me on how we take the first line of the table and make the second line as like a prediction, or like just a computation of like what percent? So then, if in this area there are 327 voters, how many of them should vote for Mr. Mears? I need to discuss with your team or yourself and try to figure out, how do we determine this Y value of voters for Mr. Mears? I'm going to give you a couple minutes to try to figure this out. Then, if you think you have that, extend it to F. If you think you have your answer, extend it to E and F. But you can leap over E for right now if you want. What do you think would be most effective? If there were 350,125 people voting, how many vote for Mr. Mears? Oh. You know. Do we think we're good? I got a question. Right when I show up to call these people, right when I get there, how many people have been called and how many people told me they vote for Mr. Mears? right when I show up. I have not done my job yet. I'm this pollster. 0. So we also have 0 and 0. So if we said that m, our slope, is delta y over delta x, I believe that we could figure out our slope here. Now, remember, if we're talking y and x is independent, y is dependent. Right? Y depends on x. Can my number of votes for Mr. Mears change without my number of voters changing?
No.
No. So y depends on x. This is our x. This is our y. Y depends on x. Votes for Mears depends on voters. There's been a lot of times in America's history where they said, well, if only more people had showed up to vote, this might have been different. But like, when nobody shows up, you don't have the votes. So if you try to compute your m, you could find a change in y and a change in x. Figure that out. And if we know that number of voters is my x, this is also an x. I'm going to recenter my board for a second because it's way off. So keep thinking, keep trying. If you are not done yet. You tell me.
0.8. Same thing. That works. You just do 204. And do that. That's your slope. You keep going up by that.
Doing okay, Sam? Does anyone think they know what equation we would end up using? George?
Didn't you do x? Well,
Don't my equations start with y equals?
Yeah. Oh no, I don't know that. Never mind. Oh wait.
Comment? How'd you get your 0.68?
Well, from 100, and I found it in 2 ways. 168, so I just timed 0.68, and I also found another way. I went upwards. I went downwards, like 50, 25, 17. Like 20, 25, 17, and I divided by 25.
Yeah.
I divided by 25, and I got 0.68.
When we do this division, now yesterday I told you can leave stuff as fractions. That's great. But if we're typing math on our calculator, decimals might be easier to type. When we do the division of voters for Mears out of total voters, we get 0.68. That is kind of like our scale factor here. The scale, or the amount of people voting for Mr. Mears, is 0.68 times however many voters we have. We did that division, or 34 divided by 50. Dude, it's math. We're not thinking realistically. We're thinking mathematically. So if you use that with 327 voters, how many vote for Mears?
222.
And no partial voters. You can't walk in with just the right arm and vote. So we'll say 222.
Wait,
Probably right. Now, some of you process through this in a few different ways. That's fine. But now, when we start working with really big values, like the 350,125 people, you have to know how to work with that. But guys, again, think to yourself, does this make sense? More than half of the people vote for Mr. Mears. That's one thing that you can have in your head. Less than 3/4, or like less than 75%. Like you can have all these statements in your head. And of course, if you get a number bigger than 350,000, it's probably wrong. Because you can't have more votes for the dude than you have total voters. Right? That wouldn't fall unless someone's cheating. So, if we go 0.68 times 350,125 people, what do we get?
238,085.
No and until the decimal point, but yeah, I agree with you. 238,085. You don't say and. So I'm going to start picking on that stuff. And takes the place of the decimal point. So when you say and, you guys, a lot of people say this wrong. Like people on TV, I yell at my TV a lot. And is a decimal point. Yeah, when politicians don't know how to read numbers correctly, that bothers me. Because when they're talking about money and they're not saying it correctly. Well, we can't talk about that right now, but there's plenty of reason. In 2 minutes, Stacy can write her name 17 times.
Really?
I don't know if that needs shaking, but that's like stressing me out. Alright. Here's your challenge. Next challenge. Use a proportion. Really, I don't care how you solve this. We want to know how long it's going to take Stacy to write her name 85 times. You can use any method you want here. I will tell you a proportion will work. A proportional equation will work. A graph will work. Standard math will work. There's a lot of ways to solve this. We are going to end up graphing this. No, stop. Quit with your poopy attitudes. When we talk about rates, do we normally have the time, like minutes, hours, seconds, on top or on bottom? On bottom. Because time, guys, give me your eyes for a second. Time is independent. Time doesn't give a hoot what we're doing. It's going to keep going. So when we have a situation that involves something and some amount of time, minutes, seconds, I know that says times and it's confusing here, but minutes needs to go on bottom. That's your independent variable. It doesn't care about you. But the dependent variable, that's just what time does. Really, it doesn't. It's going to keep going. Caitlin's all mad. How many times you can write your name depends on how long you do it for. It's dependent. I want you to start to analyze what's independent versus dependent in our situations. I use minutes, and then we can use a partial minute if we need. So the ratio you should be setting up is 17 compared to 2. What's a unit rate mean?
How much of something is in one of whatever the other thing is.
Yeah, so we find a unit rate here, 8.5 over 1 minute. So every minute, she can write her name 8.5 times. Here's another secret, guys. In a proportional relationship, and you might want to write this down. Your slope is nothing but your unit rate. In a given situation, if you're able to find the unit rate per one of something, that's your slope. So here, our slope is 8.5 times x. Now, when we go to make our graph, remember, we want to make our life easy. Do I want to make a graph that goes to 85 using $1 for every one?
Oh,
No. And Octavia, you weren't here, but I was laughing when I graded your paper because your triangle just went like way off the page. But like, you didn't need to graph the whole thing, and I love that you realized like, oh, I don't care, it's off the page. But to fix that going off the page issue, what do we change?
The whatever.
No, not the whatever.
No, I know what it is, but I don't know the name.
Well, you don't know what it is if you don't know the name.
Forgetting.
What is it that tells me how many of something fit into another something, or that this represents that? Oh, come on.
I know.
Trains have these. Cars have these. Like, a map has this.
sorry, scale.
Say it louder.
Scale.
Scale.
You mean a window?
We change the scale. So draw an XY axis or axes. Label them because some of us still need that practice of which is X and which is Y. Do we think our X, which we said is time, will need to go beyond 10? No. Because if it's 8.5 every minute, I bet like 10 or 12 minutes will be enough. So my X-axis, I could keep by ones. Guys, some of you, and I'm going to start counting this stuff wrong. I'm still being really nice to you guys. If you put a tick mark here, that doesn't mean it's 1. You have to label it's 1. Then you don't have to label any of the other ones if you don't want to. Or if you want to go 2, 3, 4, and just put a tick mark here and say 5, you don't have to have them. You have to label a number somewhere. You can't just put tick marks and assume what it is. You have to put numbers. You have to show the scale. So if I need to go to 85, 3, 4, 5, 6, 7, 8, 9, what should I make my scale? Every box could be worth 10. So we put a 10, 30, 50, maybe I do, skip a couple. Graph this. Is there a way that we could, without the graph, compute the time it's going to take? I didn't eat any breakfast. I apologize. I don't like eating during class. I didn't eat any food yet today. I'm starting to not feel very good.
Yeah, I do need breakfast.
I didn't eat breakfast.
We said our equation here is y equals 8.5x. Would the 85 times that she writes her name be the y value or the x value?
Y.
The y, right? Because the y, we've made the y the amount of names. So 85 equals 8.5x. How could we solve for the x, Chloe? Yeah, divide by 8.5 on both of our sides. And the reason I'm going to do this is to get a point that's a whole lot easier to graph. 6, 7, 8, 9, 10. This point shows that 10 minutes will give me 85 times that I write my name. That point was in the wrong place. In 0 minutes, how many times would she write her name? 0 times. Notice this line doesn't really hit a lot of those intersections. But that's okay, because we know that that's right. Like, we did the math. And then here's where we can really use our graph to answer a lot more problems. Graylin, if I asked you how long it would take to write your name 60 times. Actually, no, let me change that problem. If I asked you how many times you can write your name in 6 minutes, how could you use the graph to help you figure that out?
You could just expand the graph more.
We don't need to expand it. We already have that there.
Oh, wait, you could just put the 6 minutes in the equation.
Yeah, but if we want to use our graph, I agree with you. We totally could. Look at- Find the 6 minutes on the graph here. Go up until we reach the line. Okay, I agree. And then we go over, right? So in 6 minutes, according to the graph, it looks like we would get like 50, maybe slightly over 50. Exactly what Braylon said, though. If we want to plug it in, y equals 8.5 times 6, because remember, x is our time. What's 8 times 6?
48.
48. What's 8 times a half? Or, sorry, 6 times a half. 3, so 48. Oh, so this is 51. Our graph is pretty darn close. Now, the difference between a graph being proportional and not has to hit the origin. Remember, we've discussed this before, but I know it's been a little bit, so I didn't want to ask and put anyone on the spot. Got to go through the origin or utilize the origin. 0 minutes, I can't write my name any times. Questions on this? Because you know I'm going to ask you to do it on your own. I like how at this point you guys can predict probably everything about me in class and most of Phoenix, aside from maybe the schedule.
The schedule will never be right.
Do you guys think that at this point you're pretty comfortable here?
Yeah.
Do you now understand how the 8th graders get so weird and comfortable and come back to us? Like,
Yeah.
normally at the beginning of the year, 7th graders are like weirded out by how comfortable 8th graders are with us. And by the end of the year, you guys are like, oh yeah, I get it. Just wait till we travel. Travel's so much fun. Columbus trip people, we have booked our high adventure, like high ropes, zip line sort of thing. The first day we're traveling on that Tuesday. Nice, yeah. You can expand it out and keep going. Yeah. Yes. All right, check out 79. Beth and her father have a large model railroad. Shout out to Tim Dove. Has an amazing model railroad that goes all the way through his yard. I'll try to pull up, if you guys will engage with this problem right now, I'll pull up a video of the train going through Tim Dove's yard. Tim Dove was the teacher that taught social studies, who was my mentor teacher when I got hired. He has since retired and now works for the state doing education stuff, because you can keep working once you're retired. If you'll do this problem, I will find that video. Okay? Go for it. So that's more what you want. But if you got a book, that's what there's either an 11 or a 9 involved in there. Somebody has the denominator. So you figure out. How'd you even get it?
No, I didn't 4.6.
Right? The length of the model railroad makes the real thing. After the size of the model railroad. Clear. So if we do 2, 6, 0, run by 3, that.
If you don't have some version of this table in your notes, I would advise you quickly just, real quick, T-chart, X, Y. Oh, Lordy, I only have 5 minutes left. So, in decimal notation, what is the unit rate for Beth's railroad? And then for her uncle's railroad? So we know Beth's 260 over 3. Right? Beth figured out the equation that relates, so that's hers. But this, and some of us right now are like, oh, I didn't read this. This table shows us her uncle's railroad, which is different. Right? Different gauges, which is actually the scale. But with railroads, they call them gauges, like H gauge, O gauge. I think the one that we just showed from Mr. Dell's back there, I think that's an H gauge. So how, I'll even take a volunteer because it's Friday and I'm trying to make your life easy and comfortable. How do we solve the uncle's unit rate? Olivia? 0.94 times 60? Okay, what'd you get? I disagree. Because if you did 0.94 times 60, you'd get a smaller number.
56.4.
Oh, 56.4. Now wait, why? How is that a unit rate? Like, what would your label be? Like, something per one of something, but yeah, if you don't know, I would ask yourself, why did we do what we did? If you want, like, I'm not opposed to doing any math that you want me to do, but we got to know why. Right? To talk about a unit rate, we're comparing something to something. Right? Like dollars per gallon or whatever. Our unit rate here is comparing real to fake, to model. So if I want a unit rate, well, I need the y compared to the x through division. We do that, what'd you get? 63 point what? 1/6. Now wait, if we do the division of Beth's railroad, what's 260 divided by 3?
86 and 2/3.
So why? Who can explain what those two different equations mean? Like, not saying y equals da da da, like real stuff, model stuff. Like, who can explain what in the world that tells me?
It tells you that for every inch on a model railroad or on a model part, it is 86 and 2/3 inches in real life.
Or her uncle, keep going, you're right.
Or for the uncle, it's for every 1 inch on the, for every 1 inch for a part, it's 63.16 inches.
So be careful when I ask this question. Whose model involves a bigger train? Think it through for a second. Malarkey. 86 and 63 are not the same. Think. I told you to think for a second, and you spouted out a definite non-truth. We have different railroads, right? This is Beth.
No, Beth is smaller.
This division we did for Beth. I know. So this is Beth, right? And then over here is her uncle. Whose railroad is bigger and justify with why? Mallory? If you imagine taking the same person or the same thing in Beth's railroad, 1 inch of the model equals 86 in real life. Tall, right? Her uncle's 1 inch in the model only equals 63 in real life. So Mallory's arguing the uncle's is bigger as the model because it doesn't have as much to expand up. Now, if we wanted to test that and verify, what's the real life size? The X or the Y?
Yeah, the Y.
The Y is the real life, right?
Yeah.
Pick something. I'm going to pick myself. I am 74 inches tall. If I were to drop down into Beth's model, how tall would I be? Or if I were to drop down into her uncle's model, how tall would I be? So we got to do the math. Octavio, that's not helping us do the math. The model over there, because X is the model, right? Or the model over here, which model is bigger? The uncle. So I love Mallory's statement of her hypothetical, but if we want to test it, pick an item and shrink them both down into both models. If I shrink myself into their models, here I'm going to be 74/86 of an inch, less than 1. Here I'm 74/63, more than 1. This model is bigger as we take the same item and shrink them down. This guy's bigger. Questions? We will continue to play with this stuff next week. Please enjoy your 3-day weekend. Do something special on Monday. Don't show up here Monday, because I was about to. I didn't realize we had Monday off until yesterday. I had plans for Monday, like school plans, and now that's not going to happen. It's sad that I didn't realize we had the day off. Stop. Well, and you might not be doing stuff.
Yay!